Howdy and welcome back. So let's get into the, I guess, more fun part of this lesson and begin talking about some of the different ways to represent graphs within our applications. So we're going to focus on the adjacency matrix first. And when you think matrix, what comes to mind? Maybe a two-dimensional array. So let's go ahead and consider the graph here on the left. We can see that we have 6 nodes and we've labeled them 0 through 5. So 0 through v minus 1, 6 minus 1 is 5 as the labels. Notice that we have created a v by v two-dimensional array. So it's a 6 by 6 array. So 6 rows, 6 columns. Remember, it's 0 through size minus 1, so 0 through 5. Here's how we've structured this. We have the source over here on the left, and then the columns going to be used to denote a destination. So let's say we wanted to create a new edge between 0 and 1. We're dealing with a undirected graph. So the first thing would is to say, okay, if 0 is the source and 1 is the destination, let's put a non-zero value to sit there at that location. So row 0, column 1, to signify that there is a connection between 0 and 1. However, because we're dealing with an undirected graph, we also need to show that there is a connection from the vertex labeled 1 to that of 0. So we can see here that this green edge is represented by these 2 green entries in our two-dimensional array. So we've effectively said there exists an edge between node 0 and node 1, as denoted here, and from node 1 to node 0 here. Okay, well, let's continue building this up. If we go ahead and look, we can see I've tried my best to highlight. So see this like orange, I guess I better draw it in orange, this orange connection between vertex labeled 1 and 4. I've gone ahead and tried to show those entries in the table in orange. So we can see there exists a connection from node 4 to node 1. So again, 4 to 1, there exists an edge there. Likewise, from 1 to 4, we also observe a non-zero value in row 1, column 4, that symbolizes or tells us that there's an edge from node 1 to node 4. We kind of continue on, we can see, okay, here's the blue edges because I'm trying to color code everything for you all. So this edge right here, that's represented to show a undirected edge from a source of 3 to the vertex labeled 1. Likewise, because this is undirection, there's also an edge from 1 to node 3. Okay, continuing this process, here's the red edge. Its entries in the table are here. We can see, okay, there's an entry from 5 to 3, and because it's undirected, we'll mirror this over here on the other side. So there's one from 3 to 5. And just continuing through here, you can see how each of the edges are represented. If we wanted to insert a new edge into our graph, say, I don't know, where do y'all want to go? I guess we could do some purple here between 0 and 2. If we wanted to add that edge, all we'd have to do is index into our matrix at 0 to 2 and add a 1 there to symbolize there is an edge. And then because this is undirected, we also have to index into 2, 0 to indicate that the edge is indeed undirected. And that's all it takes to add an edge to our graph, is this direct access to specific locations within our matrix. And likewise, if I asked you, is there an edge from 1 to 4? All you have to do is go into this two-dimensional array, go to row 1, offset into that row by 4. So 1 I said 1, 4, right? I'm getting ahead of myself. So yeah, from 1 to 4, we simply hop to that location in our two-dimensional array, check if we have a non-zero value. We do, an edge exist here. A couple of things to note is that some values that are used to denote that an edge does not exist are 0. However, it's not always this binary 0 and 1. There's an idea of weight between kind of edges where you can weigh them higher. We talked about this with the social media network kind of example where we said maybe two friends have a stronger connection than another friend. So maybe this is friend 1, friend 4, and they have a connection of 10. And that between, say, friend 1 and 3 is only a 2. So it's less strong of a friendship. Within our matrix, we could go ahead and store maybe 10 on the from 1 to 4 and 4 to 1, opposed to the value of 1 or 0, and then 2, 1 to 3, and 3 to 1. If we want to do it, and there's different ways to go this. So again, 0 might indicate no connection, or alternatively, if maybe we were trying to represent, I don't know, how much these people didn't get along, maybe no edge would represent no relationship and be encoded as maybe positive infinity. So there's a bunch of different encoding schemes that we can kind of use to implement our graph. And what's important is that as we go through our implementation, we're cognizant of kind of a representation here. But we can see here there's some vast benefits in that it's very quick to look into our array to see whether or not a connection or relationship exists between two vertexes within our graph, as well as if no relationship exists amongst them. Likewise, it's very easy to add an edge in an undirected graph. It's very simple. We just have to make sure we hit both the both instances where a node's either the start, where both nodes are considered the start and destination. So hopefully that makes sense. But what you will kind of see here is the other interesting thing to note is that this representation doesn't only store the connections. Space is also allocated to store non-connections. And the question becomes, if a connection doesn't exist, do we really need to sacrifice memory to communicate that? Or could we just say, if you somehow look up in whatever we're using to represent this, and you don't find something, then nothing exists, opposed to explicitly labeling it as we've done here. Well, let's look at adjacency list and talk about that a little bit here now next. Oh, but before we do, one more slide. Didn't mean to tease you, but let's go ahead and say this adjacency matrix representation, let's prefer this mode of representation when the number of edges is close to the number of vertices squared, or when we need to quickly determine whether there is a connection between two vertices. This is essentially saying this E is close to V squared, number of edges is close to the number of vertices squared, is communicating a very dense graph. And it kind of makes sense because in that case, we wouldn't be wasting a lot of space to zeros as we would in a sparse graph. And then again, for the adjacency matrix representation of some graph G with some set of vertex, some set of edges, V and E respectively, this representation is going to require a V times V size matrix A, where each individual element of that A will use some sort of integer encoding to tell whether or not an edge exists between vertex I and vertex J, and then also to communicate whether or not an edge does not exist between the two. This representation is going to require a V squared memory, and that's going to be independent of the number of edges in our graph G, because we're both representing the edges that exist as well as the edges that don't exist between any given set of vertices presenting within our graph G. So now we're ready to move on. Hopefully that makes sense. We're going to now shift into this idea of an adjacency list for representation. And then we'll close out in the final video of the day some discussion about some of the time and space implications of choosing, say, one representation over another.